So you've taken the liberty to go ahead and set yourself up for this whole unit by filling out this first page with all the variables, the units for those variables, the conversions, as well as the definition of what those variables represent according to the kinetic molecular theory, and the illustrations that represent each of those variables. And so we're going to proceed into the second page. The kinetic molecular theory, abbreviated KMT, summarizes 5 assumptions about ideal gases. And the 5 assumptions are: ideal gases do not attract or repel each other. There are no intermolecular forces. Ideal gases are smaller than the distance between them, so they have no volume. Also, they're point masses, so essentially they're a little point with mass. Ideal gases are in constant random motion. There's no kinetic energy lost when they collide with one another. In other words, they have elastic collisions. And then lastly, ideal gases have the same kinetic energy as long as they are at the same temperature. So we're defining kinetic energy as a temperature unit. So it depends on it's temperature dependent. And so here you see two models comparing and contrasting essentially ideal gases versus real gases. You'll notice in the ideal gas they are point masses and there's no volume, not much volume to them. They're evenly spaced between each other, thus they have no intermolecular forces attracting those particles together. They are real gases, on the other hand. If you look on this side, you'll notice that they clump together, and when they clump together they must have intermolecular forces and can attract one another to become a liquid state. They're larger in sizes, and so they have volume essentially, and we oftentimes show for volume by the energy levels they are in terms of the periodic table. The first energy level versus the second versus the third. So when you do the practice, what you're looking for when you're looking for ideal gases is something that is nonpolar with weak intermolecular forces, something that is small with less energy levels, or even looking at molar mass for determining the lesser the molar mass, the more ideal a gas is. So the first example, if you go through it, you can run through which one has the lesser molar mass, and hydrogen does. It has a molar mass of 2.02 grams per mole, while helium has 4.00 grams per mole. In the second, letter B, neon is more ideal because it has 2 energy levels, while argon has 3 energy levels. Between oxygen and nitrogen, nitrogen is more ideal because it has lower molar mass than oxygen. Now, oxygen actually and nitrogen are on the same energy levels, so you can't really look at energy levels in that respect. In this last example, you'll notice that HCl is more ideal because it has DDF versus HF, which has hydrogen bonding. And then in letter E, H2S, it has dipole-dipole forces, while water has hydrogen bonding, water vapor. And then of course the last one, F, if you draw the Lewis structures, you'll notice that one is polar and the other one's nonpolar. Carbon dioxide is nonpolar, so it has LDF, while sulfur dioxide is polar and has DDF forces. So all of these gas laws that we're about to venture into are dependent on pressure, volume, moles, ideal gas constant, and temperature. Now, these gases are all assumed to be ideal, and they wouldn't work mathematically unless we had ideal gases, and I'll prove to you that the mathematics behind it later on. The first gas law is Boyle's law. Boyle's law is P1 times V1 equals P2 times V2. This gas law can be graphically interpreted as you see below the equation. In the graph, you'll notice that volume is on the x-axis and pressure is dependent on that any amount of volume. So as I decrease in or increase in volume, you'll notice that the pressure decreases. So imagine yourself squeezing an empty bottle. Now, it's not really empty, it's got air in it. So as you increase or decrease that volume of that bottle, you'll notice that the pressure feels harder and harder to push on that bottle. So the pressure is increasing. Variables that are held constant are variables that are not in the equation that are listed here. So you see P in the equation, you see V in the equation, but you do not see N, R, and T. And so the variables held constant are N, R, and T. Let's jump over to the modeling to help us to understand Boyle's law. If you look at the equation, the Boyle's law equation has P1 times V1. The 1 really means the before, and then the 2 is the aftermath after you change either pressure or volume. So in this image, here's our before and here's our after. In the before image, you'll notice a certain volume and a certain pressure. The moles of the gases stay the same. So if you count all the moles of the particles, you will count 10 particles between the before and after picture. Now, let's go ahead and focus on the actual variables that are changing. If you notice between the volume of the container, you'll notice that the pressure is being halved between the before and after. As a result, the pressure is doubled. And you can see the denotation of doubling is the doubled arrows. And so let's go ahead and do the mathematics behind this actual problem. It should align with the modeling as well. So when I do this problem, I first like to designate the variables that I can identify. So 540 milliliters is in fact volume 1, and it has a pressure 1. And then what is the pressure? It sounds like it's looking for P2. If the container, and so this is V2. And so substituting it into the equation, you'll just substitute it to Boyle's law as P1 equaling 608 millimeters of mercury. And then V1 is 540 milliliters equals P2, which is our unknown, so it's the variable we'll solve for, and 270 milliliters is our final volume. Notice how the volume units are consistent, thus the final pressure unit will be millimeters of mercury. Solving for P2, I get 1,220 millimeters of mercury, which means, class, it makes complete sense because you've halved. Notice how you have halved the volume, as this has been the case, and so the pressure doubles. So what's double 608? It's 1,220 millimeters of mercury. Let's jump over to Charles' law. Charles' law is a volume to temperature relationship. So V1 over T1 equals V2 over T2. So you'll notice graphically that temperature is related to volume. Now, volume is dependent on absolute temperature. So what does that mean? Temperature has to be in a unit called Kelvin. And Kelvin is absolute zero, where you cannot go below 0 Kelvin, and thus you can never yield a negative value for Kelvin. Because at absolute zero, all particles and anything stops moving. Everything stops moving. Matter starts moving. So If you look at this relationship between volume and temperature, they're directly related to one another. The variables held constant, once again, we're looking up here to see which variables are held constant, and it looks like the variables held constant are P, not V, N, and R. So, and not T, because T is involved in Charles' law. So we look at the equation. Let's go ahead and explore the modeling after looking at the equation. According to the model, you'll notice that temperature is increasing. And I've made it so that temperature is doubling. You'll see it in the mathematics when you get to the actual word problem. And notice how the pressure stays constant. And we know the pressure staying constant is because the arrows, the same number of arrows in the before and after, are there. And then also the moles of gases are also constant because the number of particles is still 10 here and 10 here. And so that means volume is affected. And how volume is affected, it looks like, is volume is being doubled. Now, if you look at the equation is taking volume, dividing it by temperature. So if you take volume and divide it by temperature, you'll notice that 2 divided by 2 gives you 1. Once again, you have not changed the equation when you look at the initial and the final of Charles' law. So let's go ahead and do the mathematical word problem. What will be the volume? It sounds like a V2 scenario, but it doesn't really matter whether we call it V1 or V2, as long as we pair it up with the temperature correctly. So if we call this volume 2, this must be T2. And then of course this must be volume 1, and this is temperature 1. And it says assume pressure is constant. Now, if it doesn't mention that last statement, you can still assume that pressure is constant because pressure is not changing in this problem. So let's go ahead and look at the equation. So it's V1. V1 is 3.42 liters. T1 is negative 57 degrees Celsius. Now, if I put that negative down below here, I would see that my volume, V2, is going to end up being a negative number. And that's why we resort to absolute temperature, which is Kelvin temperature. So turning this temperature, negative 57 degrees Celsius, into Kelvin is just a matter of adding 273 to it. Adding 273 to negative 57 gives you 216 Kelvin. Now let's look on the other side of the equation. V2 is our unknown. Our T2 is, once again, because T1 is in Kelvin, T2 must also be in Kelvin, and that's 432 Kelvin. Now, did you notice how the temperature is doubled? Doubling 216 gives you 432. So what do you suppose the volume is going to do? When you do the math, and hopefully you can then, I like to cross multiply in this case. Whatever you do, just solve for V2 correctly. When I do that, I get 6.84 liters. Now for Gay-Lussac's law. Gay-Lussac's law is a relationship between pressure and temperature. So P1 over V or T1 equals P2 over T2. Now let me just list the variables again to help us to determine which variables are held constant. And the variables held constant are V, N, and R. And so let's go ahead and look at the illustration, just so that we can have a good sense of what we are conceptually looking at. So temperature is in doubling, and we'll notice the moles are staying the same between the two before and after container, but the pressure has doubled as well. So Once again, if you take the equation, Gay-Lussac's equation, and take P divided by T, you'll notice that when you take this top divided by this bottom T, you'll notice 2 divided by 2 gives you 1. So you're not changing, once again, the equation in the before and after scenario. So let's go ahead and now calculate it mathematically. It says right here, what is the pressure? So I'm thinking it's looking for P2 inside a rigid tank. Now, rigid tank means that their volume isn't changing, so you're not seeing that to be an essential part of any changes. And it says it starts at, which means this is our T1 and this is our P1. And of course, it raises the temperature T2. So go ahead and substitute it into Gay-Lussac's equation, starting off with P1, 1.2 atm. T1, reminder that temperature must be in Kelvin temperature, so just reminding us that Kelvin is the unit we want. And I did forget to tell you, or you should have seen the direct relationship between pressure and temperature. And so P2 is what we're looking for. T1 is actually 270 after you add it to negative, after you add negative 273 to negative 3 degrees Kelvin. And then, of course, T2, when you add 273 to 267, you will get 540. Notice how the temperature has doubled. The temperature has doubled in the before and after. And so we should expect the pressure to double as well. When I do the math for a fraction equaling a fraction, I really do like to do this butterfly method or crisscross method, cross multiplication. And solving for P2, I would expect, as I expected, it would be 2.4 atm. So it doubled in pressure in between the before and after. Combined gas law is P1 V1 over T1. You'll notice that it is all the variables that we have come across thus far. So this is the combined gas law. And a way for us to remember all the different gas laws is like this. This little triangle helps us to remember which gas name goes with which gas law. So if you look at the combined gas law together, PV over T, if you've got B on top, if you situate B on top, it's pressure and volume. V over T is Charles' law. P over T is Gay-Lussac's law. So this is a little mnemonics to help us to remember. Now, let's go ahead and write down the variables that are held constant. It looks like moles and R are both constants. I'm going to actually go into this problem right away. So let's go ahead and designate all these variables. I see volume 1, pressure 1, at temperature 1, and it's compressed, which means the volume 2, there's some compression going on, decrease in volume. And of course, this is my P2. So it's asking for my T2. So I substitute all my variables in, starting off with P1. 723 millimeters mercury. V1, 6.20 liters. T2, 294 Kelvin units. Temperature must be in Kelvin once again. Equals, going over to the other side, P2. P2 is 2,169 millimeters of mercury. V2 is 3.20 liters. And of course, T2 is what we're solving for. Upon solving for T2, you will get 441 Kelvin units, but then you want it in Celsius. So you subtract 273, and that will give you 168 degrees Celsius. Now, the reason why I didn't jump over to the model after I introduced the equation is because there's a lot of things going on in the combined gas law. First of all, we see the pressure tripling. And then we see the volume halving. And then we see the temperature going through something. We don't know quite yet, but you can actually see the temperature going through, and it actually is 3 halves what was the original temperature. So if you do the math, multiply 3 times 1 half, you get 3 halves. But then you divide it by 3 halves, you get 1. Once again, you always end up getting 1 to show for how this beginning equation is always going to equal the aftermath equation. So it's not mathematically changing the before and after scenario. Now, Avogadro's principle involves variables, one of the variables you have not seen yet, which is moles. And so the principle states that V1 over N1 equals V2 over N2. So the more moles you have, the more volume you would have. And that makes sense. It's like pumping up a balloon. When you pump a balloon, you add more moles of gases, air specifically, and so the balloon starts to increase in volume. Variables held constant are P, N, P, R, and T. And so let's go ahead and work through what we see here. We're looking at the N 3 timesing, and of course the volume is also going to be 3 times. And once again, you take your volume and divide it by your moles, you will get 1. And so let's go ahead and do the math. Here we have N1, V1, and it's inflated with an additional, the word additional means 2 more moles than what 1 is, which now means N2 is 3 moles. And so we're asked to find the V2. And substituting everything into the equation, this is a pretty easy one to just set up. 22.4 liters over 1 mole. V2 is what we're looking for, and of course we're tripling the moles. And so what we should expect to see is this value right here tripling up. And that's precisely what happens. You get 67.2 liters in the end. And so how does the balloon's initial compare to its final? It became 3 times, and 3 times the volume. Now, Graham's law works by ratioing 2 gases and comparing 2 gases and their rates. the velocity specifically. So velocity of gas 1 over velocity of gas 2 equals a ratio of the molar masses. So molar mass of gas 2 over molar mass of gas 1. And this equation is all based off of the kinetic definition based on their velocity. So we're really basing it off of kinetic energy. And it's from the kinetic molecular theory in the sense that the kinetic energy of two gases is always going to be the same for both gases. And so the kinetic energy is based on 1/2 the mass, or molar mass in this case, times the velocity squared. And so when we compare and ratio two gases and their velocity, so we take the same equation, ratio against each other, you'll notice that this equation right here is derived from this idea. Variables that are held constant are everything. P, V, N, R, and T. And so let's go ahead and look at this problem, but let's model it first. Between Mrs. No and Shaquille O'Neal, a famous basketball player, and we're both jockeys on a horse, who would win that race? I hope you say me. And I hope you say me because I am lighter weight. And lighter gases in the same light are going to travel faster than heavier gases, molar mass wise. And so hopefully we are on the same page as this, with this. And so right here it says ratio the velocity of two gases, hydrogen to carbon dioxide. So the way they ordered this, it's really saying, hey, give me the ratio of H2 to that of CO2. And so we're going to take the molar masses of CO2 on top, and of course the molar mass of H2 on the bottom. And you'll notice that when you divide and take the square root of this number, you'll end up with a ratio that is 4.67. And what that means is it describes how hydrogen gas, the rate of hydrogen gas travels 4.67 times faster than the rate of carbon dioxide. And so where will this gas meet along this tube? If we were to put both gases, cotton balls of both gases, in at the same time. And so you'll see them meeting definitely more so on the side of the slower gas. This will be approximately where they will meet in the end, near the heavier gas, because the lighter gas will travel faster than the heavier one. So we're going to compare the difference between an ideal gas versus a real gas in an actual law, Boyle's law specifically. Now recall Boyle's law is P1 times V1 equals P2 times V2. If you look at the initial before diagram, you have volume to be assumed to be 1 liter. Pressure is 1 atm, and it's denoted by 1 arrow. The changes that will occur will be changes to volume. So volume will be halved. Notice that no longer is it 1 liter. Now it's become 0.2 liter or 0.5 liters. And so if you take a look at the volume, you will see the container size is going to be halved. We would expect between volume and pressure to be inversely related. So thus, if I halve the volume, I would be doubling the pressure. In doing so, we're going to represent the same number of moles of gases. So there are 10 moles of gases in the before image, and now there will be 10 moles of gases in the after image. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And notice that these 10 particles are spread as evenly as we can possibly spread them. And as a result, the pressure is going to be doubled. And so I'm going to draw 2 arrows to represent the doubling of that pressure. So as far as the mathematics is concerned, when you take P1 and you multiply it times V1, you will get, so P1 times V1, you will get 1 atm. So 1. So 1 atm times 1 liter will yield 1 in essence in the end. And likewise on this side, if you take P2 and times it by V2, 2 atm times it by 0.5 liters is going to give you 1 also. And so P1 times V1 equals P2 times V2. Now let's look at the real gas scenario. In real gases, unlike ideal gases, real gases are larger in volume. So if you compare the size of one gas particle here versus an ideal gas here, you'll see that the real gas has larger volume. You also see them not spaced evenly apart from each other. Sometimes they are closer and sometimes they're farther apart from each other, as you see here. What we're going to do is the same scenario where we're going to take the volume and half it in the before and after. We would expect the pressure to double, but let's draw to see what is happening to the particles. So in drawing these 10 particles in the after model, we'll notice that in drawing 10 of them, we can't help but have to squeeze some of these particles together in order to fit all 10 into that 0.5 liter container. And so in reality, some of these particles are going to condense together and become a liquid in the end. And that means there's less gas particles on top here to exert pressure. Thus, your pressure isn't going to be 2 atm as expected. It'd be something less than 2 atm. So I'm going to pick any number and I'm going to make it an even fraction of some sort. So 1.4, for instance. So when we multiply P1 times V1, 1 atm times 1 liter, and then we multiply P2 times V2, we notice they are not equivalent. So 1 times 1 on this side is not equal to 0.7 on this side. And so what ideal gases do is the mathematics works for ideal gases, as we see here. It ends up with a true statement, whereas the mathematics does not work with a real gas due to the fact that real gases have intermolecular forces and then can change up the total pressure of the system as a result in this scenario. So I'd like you to go ahead and explain what you see the difference in your own words between an ideal gases versus a real gas with respect to Boyle's law. Now, ideal gases, or when does a real gas behave like an ideal gas? So we usually try to set our conditions such that we have high temperature, low pressure, so the gas particles are moving very fast, and there's less collisions with those gas particles, and a lot of volume so that we can space those gas particles as far apart from each other as possible. So these scenarios are conducive scenarios for when a real gas behaves like an ideal gas. And so we set our laboratory conditions with these scenarios in mind so that our real gas behaves ideally and has no intermolecular forces that would cause them to change up our overall mathematical computations. So go ahead and explain your reasoning for each of these conditions. Conditions being the temperature, pressure, and volume. Back to each time we've gone through all these gas law, Boyle's, Charles, Gay-Lussac's, as well as the combined Avocados Principle. When we go through all these gas laws, we are assuming, or we are basing it off of the ideal gas law, which is PV equals nRT. Now in this equation, you're not looking at before and after changes like you see in the other gas laws. So there's not a before or after equivalence here. We're looking at basically being able to solve for either the pressure given the volume, moles, ideal gas constant, and temperature, or the volume given the pressure, moles, ideal gas constant, or temperature. Or we can figure out the moles of an ideal gas given the pressure, volume, our ideal constant, as well as the temperature. So this equation allows us to basically find information about our ideal gas straight out with its pressure, volume, moles, ideal gas constant, and temperature. So the variables held constant, there's only one really, and that is R. It is the ideal gas constant itself. So in solving this equation, we have to go through and run through and make sure that we're looking at first an ideal gas. So if this is helium, we know helium is pretty small. It's a noble gas, and it's got London dispersion forces, which are one of the weakest intermolecular forces. So looking at what's given to us, 10.0 grams, this is representing moles because we can convert grams to moles quite easily. Now we have T here, we have P here. So we're quite familiar with everything, and we're trying to solve for V. And so we're going to first take our 10 grams of helium and convert it to moles. So 1 mole of helium has a mass of 4.00 grams of helium. Now calculating and dividing that, I get 2.50 moles of helium. So now we're ready to plug it into PV equals nRT, which is the ideal gas law. So starting off with P is 700 millimeters of mercury. V is our unknown. N is 2.50 moles. R If you look at the very first page of your notes, R can be three different constants. You find the constant that has R with millimeters of mercury, because that's what really distinguishes one R from the next, is it's been converted between units of pressure. So we're going to use 62.4 liters times millimeters of mercury over moles times Kelvin. And then T is 298 Kelvin. Once again, this R constant actually tells us what the other units have to be in. So R says that pressure is in millimeters of mercury, as it is here. R here tells us volume must be in liters. So our final volume is going to be in liter units. R here, moles down here, tells us that it should be moles as far as N is concerned. And then temperature says that it should be in Kelvin. So I'm going to cross cancel many of the units that you see from the R constant between the two sides. So millimeters of mercury actually cross cancels itself. And of course, moles on the same side, as long as the top and bottom can cross cancel, and Kelvin can also cross cancel. So those units are your final units, or the final unit that is left is liters. So when you solve for V and you get 66.4 liter, or 66.4, you're also going to get liters as the final unit. So this law tells us essentially we can find out all the information about a gas as long as we have 3 of the 4 variables: pressure, volume, moles, or temperature. So now we move on to gas stoichiometry. When we're looking at gas, the word gas and stoichiometry, we are looking at doing mole ratioing with gases. And in terms of mole ratioing, going back to the ideal gas law, the variable that allows us to get to moles is N. So if we can solve in the ideal gas law for N, we can do stoichiometry quite quickly. So again, stoichiometry, the way to stoichiometry is through the mole variable, which is N. So we're going to first have to figure out why this problem right here is a stoichiometry problem. So let's take a quick read of this image, or of this problem. We have the mass of sulfuric acid is needed to react with sodium chloride to produce 340 milliliters of hydrogen chloride at 1.51 atm at 20 degrees Celsius. So the first thing to do is to write a balance equation. And how I know to do that is because I see a reaction occurring. You're having two substances react to form another substance, as well as probably an additional substance. So let's go ahead and write a chemical reaction out to start. So we've got sulfuric acid reacting with sodium chloride to form hydrogen chloride plus, now remember this is a double replacement reaction. The second substance you're forming is sodium sulfate. And don't forget to neutralize that sodium sulfate. Now we're going to balance this equation. And in balancing this equation, I get 1, 2, 2, 1 coefficients. So we know what the mole ratio is among those values. Now we then take the information and we see that we're given here the volume of hydrogen chloride, the pressure of hydrogen chloride, and the temperature. So this is a gas here. This hydrogen chloride must be an ideal gas. And so we're going to solve for if we've got pressure, volume, as well as temperature, we're going to solve for the moles. So in solving for the moles using the ideal gas law, we're going to plug in P, we're going to plug in V, 340 milliliters, and we're going to plug in N, but we don't know N, and that's why we're going to try to solve for N of HCl. R, because pressure is 1.51 atm, we're going to use 0.0821 liters times atm, moles times Kelvin. Once again, we chosen our R based on the correct constant that has the correct unit. And T is 293 Kelvin when we add 20 degrees to 273. Solving for our R, we get N of HCl equaling 0.0213 moles of HCl. Now we can then mole ratio it, HCl, to sulfuric acid. So the mole ratio is in fact for every 2 HCl, there's 1 H2SO4. So for every 2 hydrogen chloride, there's 1 mole of sulfuric acid. So we're going to put those ratios in. So for every 2, there's 1. And we're not going to stop there. We're actually going to try to figure out the mass of sulfuric acid. So a mole of sulfuric acid has a mass of 98.09 grams of sulfuric acid. And so finishing this up, I get 1.05 grams of sulfuric acid. Now when stoichiometry, usually you have an image of a mole here. And so only moles can do stoichiometry through what is called the mole ratio. So now let's go ahead and do gas stoichiometry at STP conditions. Now what is STP conditions? STP stands for standard, temperature, and pressure. And standard temperature is actually a set temperature. It's 273 degrees Kelvin, or also 0 degrees Celsius. What is standard pressure? Standard pressure is 1 atm. We like to have a set of standard conditions for experimentation. So at standard conditions, 1 mole of a gas has 22.4 liters. And how we got that is actually from the ideal gas law itself. We took all these standard conditions and we substituted into this equation, and we were able to determine that 1 mole, which is our N equals 1, has 22.4 liters. And I'm just going to go ahead and set it up, and you can see and you can calculate it from there on out. So 1 atm, plugging into PV equals nRT. V is our liters, we don't know. N is our 1 mole. R is 0.0821. I'm not going to put the units because I'm a little tight on space. And volume, temperature is 273 Kelvin. So standard temperature and pressure with 1 mole has a volume, if you calculate it, to be 22.4 liters. And this is for any gas. So this is our new conversion factor. So 22.4 liters is 1 mole in the end. Now, when you have constant temperature and pressure, you can do what is called a volume to volume ratio. So if you balance this equation as you normally would balance this equation, the mole ratio is a 2 to 1 to 2 ratio. But we can also look at it in terms of volume. So for every 2 liters, we see that there's 1 liter of, for every 2 liters of hydrogen, there's 1 liter of oxygen to form 2 liters of water vapor. So literally, we actually can see the volume containers be proportional as well. So here's 2 liters, say, in this box here. 1 liter of oxygen forming 2 liters of water vapor. So when you do this, you can actually look at this this problem with respect to the liter liter to deliter ratio. Now it says right here how many liters of water vapor will be produced if you have 15 liters of hydrogen and 8.9 liters of oxygen. So if you look at this carefully, it looks like you're given both reactants and volume of both reactants. So one is going to limit how much product, which is water vapor, will form as a result. So we're going to have to determine limiting reactants. So if you recall how we determine limiting reactants, we take your given and we divide it by the coefficient in the balance equation. So 15 divided by 2 gives you 7.5. 8.9 divided by 1 gives you 8.9. So the lower amount is in fact the 15 liters of hydrogen gas. So hydrogen gas is our limiting reactant. So we're going to start off with 15 liters of hydrogen gas. And we're going to liter to liter ratio to figure out the product. So what is the liter to liter ratio between hydrogen gas and water vapor? And that is a 2 to 2 ratio. So doing so, we then get the same value as we would expect, which is 15 liters of water vapor. Now, the second question is asking what is the mass of oxygen? So we're ultimately going to have to convert our limiting reactant to figure out how much oxygen mole-wise, and then we're going to then convert the moles of oxygen to mass. So once again, we're taking the 15 liters, our limiting reactant, and we're going to ratio our limiting reactant to that of oxygen because we want to find out oxygen. And the liter to liter ratio is 1 for every 1 liter of oxygen there requires 2 liters of hydrogen. So then we know we're at Stp conditions. So at Stp conditions, we know that there's 22.4 liters of oxygen for every 1 mole. So we can convert our liters to moles as long as we're at Stp conditions. And in doing so, we then get our mole units of oxygen. And now we're going to convert our moles to grams. So there's 32 grams in 1 mole of oxygen, so leaving us with a final answer of 10.7 grams of oxygen. Dalton's law describes how the pressure total of a system equals the partial pressure of each of the gases, or the sum of the partial pressure of each of the gases. So all the variables held constant are the following. You have R, you have T, and you have V. Now, logically, in Dalton's law, what you're looking at is saying that if I take all of these three gases, oxygen, nitrogen, argon, and I stuff it into the same volume container, the pressure will certainly be just the sum of the partial pressures of each of these gases. So whatever the pressure reading is here, the pressure reading is here, and the pressure reading is here, it will just be the sum of all of those pressure readings, because it would be the sum of all the moles of the gases that are in here exerting pressure against the walls of that container. So let's go ahead and calculate this problem. It says a flask contains oxygen, nitrogen, and argon. The pressure being exerted by each of these are the following, or the total pressure is 785 millimeters mercury. If the partial pressure of nitrogen and argon, so this is P of nitrogen, and this is P of argon, partial pressure of argon, respectively, what is the pressure of oxygen? So once again, Dalton's law says that the pressure total equals the partial pressure of all the gases that are in the container, including neon, argon, and oxygen. So plugging them all into the equation, you've got 785 millimeters of mercury for a P total. Partial pressure of nitrogen is 295 millimeters of mercury. Argon is 100 millimeters of mercury. And partial pressure of oxygen is our unknown. So subtracting the sum of these two values, the sum of 295 plus 100, gives us the partial pressure of oxygen to be 390 millimeters of mercury. Now, Dalton's law could be used when we collect what is called a gas over water. So we need what is called the vapor pressure chart because we're collecting it over water and water vaporizes. We need what is called the purple vapor pressure chart. So it's the quarter sheet that you were given. So with that information, we're then going to look at what's happening in this diagram right here. So what we see here is a reaction occurring in here. The reaction that's occurring is the decomposition of calcium carbonate. And there's a gas that is coming out of this. And the gas that's coming out of this is carbon dioxide. And you'll notice that that carbon dioxide is being bubbled over water in order to collect the carbon dioxide. So in here, in this container, is both water and carbon dioxide. Some water vapor and carbon dioxide. Now, what we do to know what the pressure inside this inverted beaker is we look at the pressure on the outside, the ambient pressure. The ambient pressure will equal the pressure total that's inside this flask. So it's inside this beaker. So as long as the water levels are equal, so the water level on the outside and inside of here, so the water level is equal, you know that the pressure inside here is equal to the outside ambient pressure. So that's why you have to equalize the water level in the inside and outside. Otherwise, they're not equal. So the pressure total equals the partial pressure of carbon dioxide and the water vapor that will vaporize over time inside this flask. So solving this problem, We read it carefully. The gas formed from the decomposition of calcium carbonate is collected over water at 25 degrees Celsius. The total pressure inside the inverted beaker was the same as the ambient pressure, which is 760 millimeters of mercury, when the water level inside the beaker is equal to the water level outside the beaker. What is the partial pressure of the dry gas? So PT equals P of both the dry gas, which is carbon dioxide, and of course the water vapor that's inside that container because it's being collected over water. PT is 760 millimeters of mercury. So this is my PT. The pressure of my gas, my dry gas, which is carbon dioxide, is unknown. The pressure, the water vapor pressure at 25 degrees Celsius, so we're going to have to look up our purple sheet, our quarter sheet purple sheet, and look at water vapor pressure at 25 degrees Celsius. And it turns out to be 23.8 millimeters of mercury. So solving for our pressure of our dry gas, we get 736.2 millimeters of mercury. So this is the partial pressure of the dry gas. So if you notice, the vapor pressure isn't going to significantly contribute to the total pressure. It only makes a small fraction of the total pressure. Most of the pressure is going to be the gas. As long as you collect enough volume, so you do have to collect a high amount of volume, and that's why ideal conditions is when the volume is high that you collected of the gas. So if you collect enough volume, you will see that most of the pressure of the container will be exerted by the gas, the dry gas itself. So we can actually calculate the molar mass of a gas using the ideal gas law. So once again, PV equals nRT. The part that's really important is the moles. So as long as we have the moles of the gas, we can calculate, and the mass of the gas, we can do molar mass. So there's a lot going on in this problem, including Dalton's law. So we're going to have to really integrate a lot of concepts, including what molar mass is. So let's review. Molar mass is mass over moles. And then if you read this problem carefully, you'll see that you're collecting a gas, the unknown gas over water. And because you're collecting the unknown gas over water, we're going to have to subtract the vapor pressure from the total pressure. So it looks like the total pressure, P total, is 762 millimeters of mercury. So we're going to then subtract the vapor pressure at 25 degrees Celsius. At 23 degrees Celsius, because the water's temperature is 23 degrees Celsius. So looking at 23 degrees Celsius on that purple quarter sheet, we see that the vapor pressure is 21.1 millimeters of mercury. So subtracting that will give us strictly the vapor pressure of the dry gas, which is our unknown gas. So this is our P of our unknown gas. So now, if I have my P, here's my V, here's my mass, and here's my temperature of the gas. So I've got all the variables to calculate
moles of gases. I'm going to use the ideal gas law, PV equals nRT, to calculate the moles of gas, my unknown gas. So let's start off with P, 740.9 millimeters of mercury. and then we shift over to V. Has to be in liters, 0.0880 liters. N, which we're solving for, and I'll label it unknown. R is the constant, and the constant we're going to choose to use is 62.4 millimeters of mercury times liters over moles times Kelvin. And then T, which is the temperature of our unknown gas, which is really our ambient temperature. 25 degrees Celsius is our ambient temperature of the surrounding, which is our unknown gas's temperature. Adding 273 to it is 298. So when then I calculate my pressure and my moles, and my moles ends up being 0.00351 moles of my unknown gas. With that, I'm going to insert it into my molar mass now that I have moles of my unknown gas, and I do have my mass. My mass is 0.20 grams. My moles is 0.00351 moles. I take that ratio and I get 56.98 grams per mole. Now, let's look at the model to help us to understand what is all going on conceptually. So if you look at the model, you're taking an unknown gas that's in the lighter and you're bubbling it into an empty, it starts off not empty, but it's full of water, no gas. And then as you collect the gas into this inverted graduated cylinder, you'll see that that gas will displace the water that was in here. And so you're able to collect the gas in this measuring tool, measuring volumetric tool called the graduated cylinder. So in the end, in this area where you see the gas, you'll see the unknown gas as well as some water vapor, because water vaporizes at room temperature. And so that's why you had to deduct the partial pressure of water from what would be the pressure inside the inverted graduated cylinder.
So we're going into revisiting an idea that we've learned before, and that's mole fraction. And mole fraction is symbolized by X, and in this case it's mole fraction of a gas called A. So if you look at what I'm about to write out, this really does make sense. If I take the moles of gas A and I take it and divide it and ratio it over the moles of total that's in the container, I should see the same proportionality with pressure. So partial pressure of gas A over pressure of total pressure of the system. So they're proportional and equivalent to each other. So now if you recall, N moles of A over N total is really defining mole fraction of A. So we can actually say that mole fraction of A equals the partial pressure of A over the total pressure. So this is we're really deriving this equation from the mole fraction, but the conceptual understanding that mole fraction is the same as partial pressure fraction in this case. So let's go ahead and take this problem and solve it. So we're first looking at taking 1.212 grams of hydrogen and converting it into moles. Because here you have grams of hydrogen and grams of helium with a total pressure of 10.1 atm. So they're linking the masses, or the moles in this case, to pressure. And what are the mole fractions of each of the gases? So I'm going to need to first calculate the mole fraction of each of the gases by converting the grams of each of the gases into moles. So 1 mole of hydrogen has 2.02 grams of hydrogen. And calculating the second one, which is helium, and dividing it by its molar mass. I then get 1.500 moles of helium. So now that I have moles of both hydrogen and helium, I can do mole fraction for each of them. So what is the mole fraction of hydrogen? It's just the moles of hydrogen over the moles total, which if you add 0.6000 plus 1.500, you should get a total of 2.100 moles. I'm going to show my work for this first step here. So this is the moles of helium, moles of hydrogen. So when you do the fraction, you'll notice 0.2857. Now, likewise, if you do the mole fraction of helium, taking the moles of helium, over its total, you get 0.7143. Now, did you notice upon adding these two mole fractions, you get 1? Because mole fraction is like a percentage. And so before you actually turn it into percentages, ratioing it out to 100, you actually get, instead of 100, you get 1. So now, to do the partial pressure of each of the gases, what we're going to do is we're going to take the pressure of A equals, or of a gas equals the mole fraction of that gas times the total pressure. So all I've done, class, is I've rearranged this equation to solve for P of A. And when I solve for P of A, I notice that I have to multiply X of A times PT. And so it's just a rearrangement of this top equation that we derived earlier. And so P of each gas, specifically hydrogen gas, is going to be the mole fraction of hydrogen gas times the pressure total. And we know what the pressure total is from the previous scenario. The pressure total, PT, is in fact 10.1 atm. So P of hydrogen gas is the fraction of it, which is 0.2857, we calculated prior, timesing it by the total pressure. And multiplying it, you get these two numbers. You get 2.886, sorry, there's only 1/8 atm. So this is the partial pressure of hydrogen gas. Now we can do the same thing for helium gas, but using its mole fraction, 0.7143 times 10.1 atm. And that equals 7.214 atm. Now, if you apply Dalton's law to these two partial pressures, in other words, You take P total equaling partial pressure of hydrogen gas plus the partial pressure of helium gas. You'll notice that those two partial pressures added together give us what we originally said was the total pressure, which is 10.1 atm. So this is going full circle in this problem. Now, if you look at the diagram, you're actually seeing the same thing where you're taking mole fraction of each of the gases and you're putting it into one container, or moles of each of these gases, hydrogen and helium, and you're putting it into the same size volume container because volume is being held constant. And you'll notice that you're adding the total moles is going to be proportional to that total pressure in the end. So whatever the partial pressures from these two exerted, in this case, hydrogen was 2.886 atm, helium was 7.214 atm. So these two partial pressures are going to be the addition and sum of those partial pressures. So however much these are related to, or the moles are related to each other, will be proportionally how the pressure is related to each other as well, especially in the total container that you see here. And that's why we can proportion out the moles as we would proportion out the pressures. Adding one last idea, variables that are held constant. So we're going to look over here and see all the variables held constant. And so if you look at the image, the model that we have on the right side, we'll notice that volume stays constant, the temperature stays constant, as well as R is constant.